Let's talk about oxidation numbers. Oxidation numbers are kind of an artificial construct that we use that are very useful to us, but we have to be careful we realize that they're not completely based in reality. What we're going to do is we're going to pretend that every atom in a compound is completely ionized. And that's not really true. We have covalent compounds as well as ionic compounds. But the oxidation numbers are very useful to us in determining who's oxidized and who's reduced in a redox reaction. So that's our goal. But in order to figure that out, we need to know the oxidation numbers. So oxidation numbers, cleverly abbreviated as ON, are going to help us figure that out. So on this page, we're just going to figure out oxidation numbers. The first and easiest rule about oxidation numbers is that an element by itself in its neutral condition has an oxidation number of 0. It has no charge. It's just by itself. If I have a piece of iron, just an iron bar, it's by itself. There's nobody else to share electrons or to take electrons or to give electrons. It is just in charge of everything, and so it has an oxidation number of 0. What if I have a compound, NaCl? This is an ionic compound, and it has a charge on the sodium, and there's a charge on the chlorine. We know that the sodium is a 1 plus, so we will give it an oxidation number equal to its charge, +1. The chloride is a 1 minus charge, so we're going to give it a -1 as its oxidation number. It's kind of odd that we write charges as, for instance, a 2 minus is how we write the charge, and a -2 is how we write the oxidation number. We turn it around. Maybe that's just so that we can recognize what we're talking about. It's a picky little thing, but that's what we do. How about iron chloride? In this case, we have iron 3 chloride, and chloride, again, is always a -1, so its oxidation number is -1. In this case, iron has a charge of 3 plus, so we're going to put +3 for its oxidation number, which we generally write underneath the element. Okay, so far, so good. What about, however, covalent compounds? How about C2H6? Now, the most useful thing in determining oxidation numbers is to realize that hydrogen is almost always a +1 and oxygen is almost always a -2. That will hold you in good stead for the majority of what you have to figure out. There's exceptions to that. Hydrogen is not a +1 when it's in combination with a metal, so it's like calcium hydride, but that's kind of unusual. We don't run into that a lot, and it'll be obvious when you do. Oxygen is almost always a -2. It's not in peroxides and it's not in superoxides, but we don't run into them very much either. So we're going to, in general, just go with hydrogen's a +1, oxygen's a -2. So let's put in the hydrogen. It's a +1. There are 6 +1s. So 6 times +1, that's for the hydrogen. That's going to equal a +6, right? So carbon, there are 2 of them, and we don't know what its oxidation number is. It's going to equal something. Okay, this whole thing has to add up to 0 because it's a compound. It's a neutral compound, so it has to add up to 0. What does this have to be? To add up to 0? Well, to add to a +6, you must have a -6 to get it to add up to 0. So each of the 2 carbons must be a -3. So if I have a -3 taken twice, a +1 taken 6 times, that will add up to 0 overall. Let's do a couple more because this may not be too obvious yet, but it will come. Here's ammonia. Again, we can start with the hydrogen because we have this little box that tells us the hydrogen is almost always a +1. If there are 3 +1s and only 1 nitrogen to make up for that, and this has to add up to 0, remember, because it's a neutral compound, This must be a minus 3. Now, it's not so hard. What if we don't have a neutral compound? What if we have a polyatomic ion? Let's say nitrate. Okay. In this case, it doesn't add up to 0. It all adds up to minus 1 because that's the charge on the polyatomic ion. Now, going back to our little box in the middle, we have hydrogen is plus 1. There's no hydrogens here. How about oxygen is minus 2? Let's put that in. Minus 2 for oxygen. There are 3 minus 2's, but instead of adding up to 0, I'm adding up to minus 1. So I have 3 times a minus 2. That gives me a minus 6. This whole thing has to add up to a minus 1. So my other piece that's missing here must be a plus 5. Since there's only one nitrogen, that nitrogen has to take all plus 5. Now, notice that I have a plus 5 for nitrogen in nitrate. I have a minus 3 for nitrogen in ammonia. Nitrogen can vary anywhere from a plus 5 to a minus 3. It can be a minus 2, a minus 1, a 0, a plus 1, a plus 2, a plus 3, a plus 4, a plus 5. And if you look on a periodic table, it's kind of neat because nitrogen is 5 away from a noble gas going one direction, and it's 3 away from the noble gas going the other direction, and that's the range of oxidation numbers that are allowable for nitrogen. Nitrogen is our flexible guy here. We're going to assign the hydrogens and the oxygens first, and then we're going to let nitrogen fill in the gap. Nitrogen really does not have an actual charge of plus 5 in nitrate, and it doesn't actually have a charge of minus 3 in ammonia. But this artificial thing called oxidation numbers is very useful in determining who's oxidized, who's reduced in redox reactions. And so even though it's kind of artificial, we're going to go ahead with it. Let's do another example. What about a phosphate ion? Phosphate is minus 3 overall. And our little box in the center of the page tells us that oxygens are generally a minus 2. We know we have 4 of them. So my little note keeping down here, which is not necessary, I'm just doing this to be hopefully helpful, is 4 times the minus 2 is a negative 8. So I have to add up to a minus 3. What must my other thing be? It must be a plus 5. So I'm going to put a plus 5 for phosphate. Let's do nitrite. Okay. Minus 2 for the oxygen. There's 2 of them. That's a minus 4 altogether, right? Has to add up to a minus 1. So a plus 3 will do that. 1 plus 3, 2 minus 2's, adds up to a minus 1. So there are oxidation numbers for nitrite. Let's do one more covalent example. C2H4F2. Oh, we haven't had any F's up till now. Fluorine is the most electronegative element in the periodic table, so he always gets his way. He gets to be a minus 1. Hydrogen is a plus 1. I have 2 minus 1's. I have 4 plus 1's. So my carbons must each be a minus 1 in order to make this add up to 0. Let's check it out. Does it add up to 0? 2 minus 1's. 2 times minus 1. 4 times plus 1. 2 times minus 1. So I have a minus 2, a plus 4, a minus 2. That all adds up to 0. It sure does. Okay, so that works. This is something that becomes really easy with practice. So I recommend that you do quite a bit of practice on this, and you'll find out that it is not nearly as difficult as it initially looks.